Yeah, we can see.
All right. Okay, good. So this, I was told that this was more descriptive complexity topic, but this is going to be squarely in, I mean, I'm more interested in circuit complexity, and sort of I thought I'll tell you about a very interesting topic slash result for an area of research, which sort of lies at the intersection of descriptive complexity and circuit complexity. So in general, just to let me just start. I mean, I don't know how much of how much you are familiar with computational complexity. In computational complexity, you are so what is so what do we really do in computational complexity? What is uh, okay? So briefly, the plan for the lecture is going to be as follows. Like I'll first talk for 50 minutes, and then we'll take like a 15-minute break, and then I'll continue with the next 50 minutes. I hope that's okay with everybody. So, so computation complexity is an area of math slash CS, where we math slash CS, where we care about, where we would like to understand uh, how much resources uh, and I'll come back to what I mean by resources here, are required to solve a particular problem, right? Yeah. And in general, resource can be anything. I mean, it could be, for example, the time required by a program to solve. Of course, when you're required to solve a problem via a computer, important. Hence the name computational complexity. So you could talk about time. You could talk about, like, let's say maybe space, right? And there are other resources, like for example, the number of uh, so let's say, for example, the number of if your algorithm is allowed to use randomness, the number of random bits uh, that you're going to use, that it's required to solve this problem. Um, or for example, of course, time and space are the usually two more well-studied notions, right? I mean, like, of course, this famous P versus NP question is something about uh, a time complexity of a certain problem, in particular the 3-SAT problem. Right? You know that if I gave you a solution to see 3-SAT is an example of a problem which belongs to NP. If I told you that, I mean, if I gave you a 3-SAT instance and gave you a solution, you can quickly verify in, when I say quickly verify, efficient in an efficient algorithm which utilizes less time to polynomial amount of time to verify that it is indeed a satisfiable 3-SAT formula. Whereas actually finding one, we don't know how to do it quickly. Like when I say quickly, what I mean is polynomial time. Yeah. So and but there could be other resources you can be concerned with. For example, if you're thinking about a distributed program, like a problem distributed algorithms, maybe the amount of bits communicated between different parties, and this is so communication could be a resource in your for your problem, right? And or other sometimes you have a large amount of data, and all you care about, you don't really, computation wise, it's not really an issue, but like really all you care about is the number of queries you make to your data, right? And this is again, number of queries could be a resource. This is the number of queries, uh, communication, number of bits communicated, or in sometimes there's also this notion of parallelizability, right? I mean, so let's say, for example, you have this problem, and you know how to solve it efficiently, but somehow it's inherently sequential, but you have a lot of computing power at your disposal. So maybe if you could break your problem into chunks and have your different computers or different processors, so to speak, solve it, then maybe That's again a resource. How much parallelizable your problem or your algorithm is, right? But in this particular course, I'm going to be concerned with just these two measures, like space and parallelizability, and I'll sort of introduce a few models of computation which are relevant, which sort of capture this notion of space complexity or parallel complexity, and we'll go on to see like a very in what in my opinion is a very surprising result, and sort of also says this why complexity theory is sort of like very difficult. Yeah. So um, okay, so in particular, the guiding question for our so by the way, feel free to interrupt me at any point during this session. So like I'm going to be I'm going to go quite slow, and if you have any questions, please feel free to interrupt me. All right. So okay. So the main question that you're going to be concerned about is well, what can you compute with a constant amount of memory? I think I already mentioned this in this abstract. With the constant amount of memory. It's not constant amount of memory or space. Yeah. And in particular, so this is not clear. I mean, so firstly, this question is not very, it's slightly very vaguely posed, right? So because, you know, it's not even clear how does constant memory computation even make sense, right? Because even indexing an n-bit string takes if you even just want to look at a particular bit, right? Even indexing an n-bit string takes log n space, right? Like you need to, I mean, if you had an n length input, like even to index a position in the string, you need like something like this omega log n space. Yeah. And also it's not clear what, so for example, what are you allowed? What is your, so it's very important that you talk about a specific model, right? I mean, so in particular, you want to know whether are you allowed, let's say, random access to your input, right? Random access to your input. And in particular, there will be this one specific, in fact, the final goal of this series of lectures is to understand the space complexity of one single function, and that's going to be this function probably which you've seen before. It's called the majority function, right? And so what is it? So majority were defined over strings of binary strings, right? So it's exactly the following function. It just asks, well, it's the set of all strings where the number of set of all binary strings where the number of ones is larger than the number of zeros. Yeah, the number of ones is strictly larger than the number of. I denote by this notation. Yeah, the fact that yeah, the count of number of ones I denoted by this sharp one of x. Yeah. And so our main question for the next couple of days is going to be okay, so is there an algorithm, is there a way to compute or decide the majority function using a constant amount of constant, using an algorithm which runs in constant space. I see the constant amount of space, right? Notice that if you, because so on n bit strings, if you gave me a string, let's say, which is x1, x2, if I give you an n bit string, the number and a binary string, the number of ones in this is going to be at most, let's say, log n, right? So at most n, right? And this number n, you can represent it using order log n bit string. In fact, no, why order? Just right. I mean, like just log n. Maybe I need a flow plus one bits of information if I'm allowed to store. Then I can, of course, compute the majority function. Yeah. So the question is, can I do this with a constant amount of space? Yeah. I hope the question, the main, so this is like going to be our guiding question. Like we're going to always be looking to answer this question. And okay, all right. So like I said, like the model is very important when you talk about such things, and usually traditionally whenever we speak about constant space algorithms, one thing that uh, if I hope predominantly you're all computer science students, so I hope that whenever you say constant space algorithms, the first thing that should come to your mind is finite state automata, right? This is the first or the the uh, this equivalence is what you study in an introductory theory course, finite automata. Uh, so let's just revisit our question to see whether this is possible, right? I mean, like, is majority uh, so is there a way this majority language can be computed by a finite state automaton? So
No.
sorry, was there a
No, no,
question?
no. I just said no because you Pumpi lemma, you can show that. Yeah.
Yes, 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 exactly, yes. I mean, no, actually, so let me actually leave this as a small exercise. So yes, like Kamal said, like pumping lemma, you can use pumping lemma to show that this is not the case. So for example, use this is a famous language. I mean, like the first non-regular language that you study is this language of this set of this language, which is whereas m is strictly greater than n, right? Like so this language is not regular, but of course this majority contains this language, right? I mean, so uh, it's not exactly this language. It has more strings apart from this, right? So let me call this L. So L is of course a subset of the majority language. But of course, this does not immediately show that because I mean, every language L is a subset of sigma star, right? But sigma star is regular. So uh, yeah, but of course, uh, anyway. So but then majority is a non-regular language, and yeah. So I'll leave this as an exercise to finish the full. I mean, like it's not particularly hard, but prove uh, the majority uh, cannot uh, be recognized by a finite automata. It's you can just I mean it's essentially the pumping lemma, but yeah, by df. Okay. Uh, all right. So all right. So okay. So but I thought like okay maybe I want to like maybe I want to like actually introduce. I was not sure whether everybody was familiar with finite state automata. So, but I hope everyone is like. So let me just give a couple of examples, like just to sort of what I'm talking about when I say finite automata, just to reinforces connection with finite memory algorithms. Yeah. So you have, I mean, let's do this by an example. Uh, okay, so here's an okay. So in financial automata, you just you have very vaguely you have a set of some states, and so you're deciding some language L over an alphabet, and an alphabet for us will be always sigma, like a binary alphabet. Uh, uh, so you have a set of states. You have some. So you have this. Transition function. Transition function, and you have a bunch of final states. So here's, let me just give you an example, which is probably easier to understand. So here's a very simple example of a finite state automaton. Yeah. So what does it do? It just well, it's a two-state automaton. Whenever it reads a 0, it stays in the state Q0, and whenever it reads a 1, it transitions to the state Q1. And again, if it reads a 0, it's in Q1, it stays there. So whenever it's reading a 0 at a particular state, it doesn't move. It only moves when it reads a 1. Yeah. So this sort of like and this is what I would call a start state. This is a start state, and this is an accepting state, which is denoted by this double circled state. Right. So why is this finite memory? Why is this an example of a finite memory algorithm? Well, in a finite state automaton, the only thing that you remember at any point is like what state you are in currently, right? Like you don't like, so as a result, really the only thing that you have to remember, and the number of states by the name finite automata here, what I mean is like the number of states is finite. So number of states is independent of the input being read. It does not grow as a function of like the length of the input. Even if you're reading like 100-bit string or 1,000-bit string, it's still the same algorithm, same two-state automaton which is going to decide. And in fact, this particular automaton, so what language does it decide? It's the parity language. So this language parity, which is set of all binary strings which have number of ones is odd. Right? Okay, good. Yeah. So I hope everyone has seen what's finite automaton is. So as a small exercise, I think should also probably which should be directly clear. If you define this language mod k, which is exactly the same thing, except the number of ones in this string is 0 mod this number k. Okay. Again, there's a simple finite state automaton for this. Okay. One small exercise I would like to think about is like, what is really so if I give you a k-state automaton, how much memory is used by k-state DFA, right? Like a k-state DFA. Right? How much memory is it really using? Is it k? It's more like log k, right? It's like, because if you want to encode the only thing you remember about that you have to remember in this algorithm is the number of states. Like sort of the memory requirement is somewhat like log k, right? Like if you are to simulate this a DFA, right? Okay, so okay, all right. So and like we saw already before, there are the languages that exactly are recognized by finite automata are regular languages, which already might know. And a nice tool for proving that a language is not regular is pumping lemma, and so you know that this language, for example, is not a regular language, right? So it's yeah. All right. So yeah. All right. So for this course, like we're going to look at a slightly more relaxed notion of memory. Uh, yeah. So we are going to we need uh, a more relaxed. Not need. I mean, we're going to introduce a few other notions, and these are sort of relaxed notions of uh, uh, constant space algorithms. Okay. And so what are they? So to do that, I'm going to sort of introduce this notion of computing itself, and I'll call this uh, a non-uniform model of computation. So what is a so let me I'll define what these are. Models of I'll define. So we're going to look at a few models which are called non-uniform models of computation. Like an So just to contrast what we saw before, this finite automaton is a uniform model of computation. So what is it? So in a uniform, so basically in a uniform model, in uniform model of computation, right? So which is basically uh, so model of computation for me is like something like an algorithm, right? So I consider DFA as an algorithm. So it's like, so you have like one algorithm. There is one single algorithm which which solves a problem, like the given, so whatever problem you want to solve. For example, parity. In this case, the previous example that we saw, there was a single DFA. It's which computed this, or whatever, which decided this parity language. Right? So there's a single algorithm which solves the language or problem. I use these terms interchangeably on all input lengths, right? Right, be it input of length 10 or 10,000, whatever it is, it's the same algorithm that solves this problem. And in the non-uniform model, we just break this, right? I mean, we say that, okay, so how do we break this? So, well, if you look at your language, you can consider your language, for example, look at the parity language. So you can think of parity language as a union of infinitely many languages, right? Let me call it ln, where ln is nothing but L intersect. So by the word, so what do I mean by this notation? Well, ln exactly consists of those strings which those n length strings which are there in the length n strings which are there in your language. Okay, so you can think of it somehow as like slicing your language into pieces, and each piece has only consists of strings of length n. Yeah. Okay, so this is another way of saying it as a set of all x belonging to 0 to the n. Okay, so I shouldn't use sigma. I mean, for me, sigma is always 0, 1 throughout this. Uh, okay. Uh, maybe it's a very redundant, not necessary. I think this first line is probably okay. Anyway, so okay. All right. So okay. So okay. So what is nice about this? Okay. So you have ln. So your language L is now divided into ln. And now what you say is for every n, like for every ln, you have this algorithm an, uh, which an which solves ln, right? So this is like sort of like a very relaxed notion, right? I'm not asking you to give one single algorithm which solves a problem, but like you're allowed to use like come up with different algorithms, a1, a2, and so on. And so for example, if you have L1, L2, L3, and so on, and then you have these algorithms A1, A2, A3 solving these, and you don't really require them to have any, I mean, it could be completely different. So the way A3 solves L3 could be completely different from the way A2 solves L2. Yeah. So 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 this is exactly the idea behind non-uniformity. So sort of like you give uh, a lot of power to the algorithm designer. Yeah, so and hence you can. Yeah. So why do we do this? It's like looks like a bit strange. I mean, why would you require something like this? Like, there are many practical ways to motivate this. One of them is that, like, after all, like whenever you're designing an algorithm to solve a problem, usually your length is for all practical purposes, like the size of the instance is bounded probably by the number of bits in your computer, right? uh, so that is one reason, and the other one is sort of like when in complexity theory, sort of you want to study which problem is hard versus which problem is easy. Sometimes it could be that maybe the real source of hardness of the problem is that the instances of different lengths are very disparate, right? Maybe instances uh, of length 1,000 behave very differently from instances of length like 10,000, let's say. Yeah. So, right. So maybe it makes more sense to have sort of different algorithms for different. Maybe up to length 1,000 you do this. After this you do something else, right? And finally, in many cases, like sort of this non-uniformity also factors in things like it's sort of like factors in things like pre-processing, which is often uh, available to you if you're a practitioner, right? I mean, there is a lot of practical things about your lens, which you can encode, and which which you can sort of like have maybe a lookup table or something like this, which kind of gives you a lot of information about this problem. Like maybe you can simplify instances in certain way, and the way you simplify instances of length 1,000 are different from the way you simplify instances of length 10,000. Yeah. So there are many reasons why this non-uniformity is sort of like nice. But really, for us, one of the main reasons is going to be that it is somehow brings. I mean, it somehow uh, uh, gives more techniques, gives more uh, techniques, and these techniques are often fairly combinatorial and also algebraic. To reason about uh, this complex. I mean, reason about your model, reason about the model. Okay. So all this is admittedly very vague. So let me just go and give you an example of a couple of non-uniform models of computation. So here's so the first non-uniform model that you're going to consider is what is called a branching program, and this is going to be a direct, I mean, generalization of. So it's going to be a direct generalization. It's going to be a non-uniform analog of the finite automaton that we just saw. Okay. All right. So so what is a branching program? Well, uh, so a branching. So again, let me do this with an example. So we just saw, uh, so let's look at a non-uniform. So we saw this language parity. So let's look at a non-uniform algorithm for parity, how it might look like, right? So for example, so let's look at the parity function on 2 bits. And this is the parity function. So it's going to be 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0. So whenever there's odd number of ones, right, then my function is this is my function value on the right hand corner here, right? So how would the non-uniform analog look like? So it will start reading. I mean, it's not very different from the uniform model. I'm just giving it uh, a way to just look at your execution or like a run of your automaton on length of on inputs of length n. So it's going to look something like this. You start at let's say the start state. Okay, there's a state, and you're going to maintain 2 tracks. Okay, and so what do you do? First, you read this variable x1, the first bit of you give an input string, and your input string, I'm assuming, is of the form x1. It's read from left to right like this: x1, x2, x3 up to xn. It's an n-bit input string. And in this particular case, for the 2-bit case, like maybe what you would do is you'll first read let's say you read a 0, and then you go to the state, right? And then again, if you read a 0, well, then you know that the parity is finally 0, so you don't, yeah, so maybe I'll call this a reject state. Okay. And what if you read a 1? Well, you read a 1, you transition to the state. This is some state, I don't want to name it right now. And if you read a 0 here, now you know that there is only odd number of zeros, so you can accept it. And what about here? So again, when you're at the 0 line, so these 2 tracks, they somehow maintain what is your current parity of the input bit read so far. So here, so now if you read a 1 here, you should transition to an accept state because you read a 0 in this path, a 1 in this path. That's totally an odd number of ones. And similarly, but here on this line below, if you read a 1, then now you have read an even number of ones, so you now reject this input. Yeah. So this is sort of like a simple representation of how your automaton would have decided a run of your automaton, right? If you just unroll this automaton into how it would behave on n bit inputs, this is exactly what it is. Like here it is 2-bit inputs, but in general, what you can do is this ladder sort of construction. You can just extend it, right? So what do we do? So it's the same thing. If you read a 0, if you're at the 0 line, so this I'll call this the 0 line. Maybe and it's the same thing as before. It's like when you read a 0, 1, 0, you keep going. Um, yeah, and you keep going until if you reach the end of the input. In this, you read xn. In this last thing, the previous you're reading xn, and based on whether xn is 0, 1, yeah, you have this thing, and this is going to be your accept line. So this is your accept, this is your reject. Yeah. So this is essentially what I've done is like sort of unrolled your automaton or how it's going to look like on length and inputs. There are a few things I did here. So you might ask why, what is this? Why is this even necessary? Um, so because in a non-uniform model, you're talking about only this particular program working on inputs of length n. One thing you need about your model is, so this is basically a graph, like just like an automaton, this is going to be a graph. Uh, but it's going to be actually a DAG, in fact, like a directed acyclic graph, right? Because if you had cycles, then then sort of like you can read inputs of longer and longer length, and in this non-uniform model, we don't want to do that. We just want an algorithm which only works for n length inputs. Yeah. So so this branching program is essentially a DAG. So you have a specific start vertex, like which I'm going to call a source. Yeah. And these two, they're going. I'm calling them sinks. Right? There are no. So the source vertex has like yeah. So I mean, I've written an incoming arrow here, but in general, it has no incoming arrow. It has only outgoing arrows, right? And similarly, the sinks have no outgoing arrows, just have incoming arrows. So a branching program is nothing but like a DAG. It's like it's a directed acyclic graph, and with the distinguished source and sink vertices, right? And the sink vertices are partitioned into uh, uh, sinks are partitioned into accept nodes and reject nodes, right? And every other node is what I call an internal node, and this internal node is going to read a variable, and based on whether this variable is 0 or 1, make some transitions, right? So here it made a couple of transitions. I mean, for example, when it was in the 0 line and it read a 1, it jumped to the 1 line, and so this is here. This is a 1 line, and this is a 0 line. Yeah. Okay.
I have a question.
Yeah.
So, so since it is, can you also say that every every DAG of this kind,
Yes.
if you look at a path from source to sink, it will
Right.
be exactly length n?
So good point, great point. So not necessarily. Yeah, I was about to come to that. Like, so the main difference between, so this was a DAG this was a branching program that came directly from an automaton. So sort of like it just read a variable only once. But in general, in a branching program, you can read the variable multiple times.
Okay.
You can read. So you can, for example, you can have a DAG where, like, in the beginning here it reads x1, and then maybe it reads x1 again here.
Yeah.
Right, and then make some decision. So all that is allowed. Yeah. So that sort of adds to its power. And yeah, thanks for pointing out.
All right.
Yeah. Okay. So, and how does this branching program accept or reject an input? Well, for any given input, this branching program naturally, the input naturally defines a path from the source to the sinks. Okay. And based on whether this, on a given input, it led to the sink or led to the source, you either accept or reject. Yeah. So for example, in this particular string, in this particular example of this parity, so if you had all zeros, then it would lead to this reject sink node, and your input is rejected, right? Clearly, as it should be. And otherwise, if you had an odd number, maybe you just read a 1 in the beginning and then everything else is a 0, then this of course gets accepted because there's exactly one single 1 in the input. Okay, so all right, so okay, so whatever, so let's so whenever you have a model of computation, like an important thing that you talk about is what is the resource, what is the resource important for this? What is the resource of this model, right? What do you want to conserve? What do you want to optimize? Right, like whenever you, so when you write a program, like you initially saw things like time, space, and so on. So those are for like programs where, like, you have like registers and so on. So in this model, what is really the cost? How do you measure cost of an algorithm in this model, right? Again, in the finite state automating, could have been like the number of states, right? So there are two parameters of interest here, and they are width and length of the branching program. Yeah. So the width of this program is basically the number of, okay, so before I define width, let me talk about what is called a layered uh, branching program. Yeah. So notice that in this example, for example, every node in this, so this is a DAG, and it has a set of vertices, but every the set of vertices can be partitioned into sets. Okay, so for example, this is partition, especially what is called layers, right? I mean, like, so every vertex is belongs to a particular layer. Yeah, you start with the first vertex, and this is layer, let's say layer 0, and this is layer 1, layer 2, layer 3. So layer 1, layer 2, layer 3, and so on, and up to layer n or whatever. So in some sense, you partitioned your set of vertices into layers in such a, what are these layers? Well, the edges go only between these layers in the stack, right? So there is no edge between, let's say, layer 0 here directly into layer 2 here. But if you generally define, the way I've defined a branching program as a DAG with just the source and sink nodes and the internal nodes, this is not clear that there is such a layering. I didn't exclude, jumps like these. Yeah, in a layered branching program, essentially you don't have such jumps. Yeah, you have only edges going between adjacent layers. Okay, and a small exercise like uh, uh, exercise, every branching program can be layered, right? I mean, there's a trivial way to uh, layer a branching program. I would like you to figure out what is the, okay, so now I come to these two measures, width and length. So length of the branching program is pretty straightforward measure. So it's like the longest path between the source and like the sinks. Max length of any source to sink path. Yeah. What is a width? Well, width is the maximum number of, for example, in a layered BP, it's the maximum number of vertices in any layer. Yeah. So why is this? I mean, if your branching program wasn't layered, then it was sort of ambiguous to define. I mean, you don't know. So basically, you don't have a definition of layer, right? So, and the notion of width sort of, yeah. I mean, it's very intuitive in the sense that it's just basically how fat your graph is, sort of like how many vertices that you have to necessarily place in parallel, right? And yeah, so and there's the notion of width. So by definition of width is, I've defined this for this layered BP. So just a short exercise, just convince yourself that, like, you can always layer a BP, like a branching program. Yeah. And figure out what is the, what is really the, how much what is the cost incurred when you layer a, if you have like a branching program on n vertices, then what is the worst case width length? Yeah. So just think about it. It's not, it's just a very simple exercise.
Yeah. So I have one question. So
Yeah.
if it is not layered, yeah,
Right.
Let's imagine because right now the way you have drawn this example,
Right.
the between layer 0 and layer 1 it's x1, between layer
Right.
1 and layer 2 it's x1, and so on. Yeah.
Right. Yeah.
So but if you have things jumping,
Right.
then I mean, what are the edges labeled with?
So it's not necessary that so for example, in general, in a branching program, this layer can read x1. So this node can read. So only thing I require is every internal label, internal node, it queries a variable, and based on whether it's a variable 0 or 1, it goes somewhere. It so happens that here both these nodes read x1, both these nodes read
Okay.
read x1. But
Okay.
in general, it could be anything. Right? It can, in general, for example, let's look at this small example here. So maybe it's something like, I start here. If x1 equals 1, in fact, okay, so let me, so good point. So let me come to this. So it could be that if x1 equals 1, I do this. And in fact, it need not be that, so, okay, in general, x1 equals 0, I do this. And here, if x2 equals 1, and or maybe what I do here is if x3 equals 1, right? So if x1 equals 1, maybe what I do is I completely ignore x2. I just go to this, right? And then here, maybe I label this as 1, 0. So this is a valid BP. It computes a function. And the function is exactly, in fact, x1 and x3, or so this is in fact actually a decision tree, which is a simpler case of a branching program, or x1 bar and x2. Yeah. So this is exactly, so just if I just collected together the what the leaves which are labeled by 1, and I just collected together the the settings which led to this and translated it into a Boolean formula. So this is exactly what this branching program is labeled by. But this is exactly the function the branching program computes. So in general, it's not necessary that in a particular layer you have to query exactly the same variable or and so on. But there are normal forms, and I invite you to think about this. You can layer the branching program as you like and enforce these normal forms into your branching program. That in every layer you're reading just only one variable, right? And all these things you can enforce. Yeah. So does it answer your question, Amal? So
Yeah.
okay. All right. So
So hence you can already compute non-regular things, yeah, because you can
yeah,
check x1 and x n by 2, x2 and x n by 2 plus 1 and so on.
right. Exactly. Right. You can already do non-regular things. In fact, the weird thing about non-uniform, so models of computation, so is like weird thing about non-uniform models of computation is that a weird property of non-uniform models is that you can decide the halting problem. Every computer, anything is computable in this model. Why is that? Well, if I only require that, I mean, if I don't require any similarity between sort of my algorithm 1 and algorithm 2, what I can do is, so of course, I hope I don't want to jump ahead too much, but just for people who understand this, the halting problem consists of all binary encodings of X encodes a halting Turing machine, right? And X encodes a halting Turing machine. Yeah. Now, of course, this X corresponds to a particular natural number, right? Naturally, you can interpret it as X as let me call this as a natural number that X encodes, right? Now, a simple non-uniform algorithm for the halting problem or any problem, any function is like, basically it just it's a trivial algorithm where an is uh, just one exactly for those n which encode uh, for those that exactly there's so okay so I'm sorry, so what I want to do is like I can take this halting problem and convert it to a unary halt. Let me call it which is should I write it somewhere? So let me call as uh, exactly uh, it's 1 raised to x, right? Such that where x belongs to h. Yeah.
So the length of x, yeah.
Yeah. So I mean, I denoted this this to mean that, but not length of x actually. It's like some natural number encoding of x, right? I mean, like x, you take x, like which is a binary number, take a binary encoding,
Okay, okay.
and you convert it to it naturally stands for some binary number, like it's a natural number encoded in binary. Now take look at this unary encoding, right? And that encoding exactly, well, there is a one-to-one mapping between these encodings. And now once you are at this unary encoding, well, you just need to remember what is by definition of a non-uniform model. We needed uh, I mean, we are allowed, rather not needed, we are allowed a different algorithm for different input length. We are allowed a different algorithm for different input length. For every input length. Yeah. So trivially now, for this, but I mean, trivially now you can encode, right? Because for every given input length, the unary problem has only one string, and either that string is in the language or not in the language, and you can just give this information right away, right? So it's a very trivial, in a very trivial sense, this is this is desirable. So as a result, non-uniform models are very powerful. So you might ask again, like, why is this like non-uniform? And they are, I mean, yeah. So they have this weird, powerful thing where they can decide the halting problem. But still, as it turns out, you can. So they're still nice in the following sense that there are ways to enforce uniformity conditions on these. Yeah. Uniformity conditions on these models, right? And yeah, so and that's so we'll probably see this towards the end of this lecture, which makes sure that you don't by chance compute. I mean, you don't come up with a crazy model which is deciding halting problem. I think. I mean, here of course you do, but like you don't use these models as a serious proxy for like designing algorithms, right? All right. So okay. So as a result, like already you can, like as Amal noted, you can already see some non-regular languages you can compute if you have these models. And in fact, so here's
By the way, I didn't understand why you need to convert it to unary. Why can't you just take all those binary strings which encode halting Turing machines and, for instance, in this case, construct a straight line programs that accept those strings? You can do that, no?
Yeah, you can. Yeah, right. You can do that. You can do that. It's just okay. So yeah, you're right. You're right. You can do that. I mean, it's just so this somehow had to do with my idea of like this efficiency. So I wanted to say that if you convert it to unary, then you had an efficient program in the sense that so the way you said what will happen is like, so that's what you're coming to next. You can encode any Boolean function into a non-uniform model. So in particular, yeah, so any halting problem or anything, whatever, but the size will be large. So for example, if you had to encode I mean directly from binary, what you would do is you would look up all binary strings of that particular length and then say whether, and just encode the truth table, right? I mean, the truth table is just is it, so what's so essentially what Amal is saying is that so you encode so you take halting problem and you write it as a union of length n subproblems, right? Like where n hn is basically all halting instances, all strings of length n which encode halting Turing machines. Yeah. Now, once you have this, you can define this function. Let me call this fh from 0, 1 to the n to 0, 1, right? And the function is exactly fh of x equals 1 if and only if x encodes halting Turing machine. Yeah. And sure, clearly, I mean, so this function, you can clearly encode it. So this is a truth table encoded by 2 to the n bits. You can 2 to the n bits suffice to encode this whole truth table. Yeah. And as a result, I can just, I mean, my algorithm AN, the non-uniform algorithm AN, or a branching program, whatever, oops. AN is just look up FH. So, right. So basically, I mean, basically, you can just encode all these 2 to the n possibilities into your algorithm, right? I mean, just if you're allowed a different algorithm, you can just encode all these 2 to the n possibilities, which can be encoded by exactly 2 to the n bits, and that will be just your algorithm, your branching program. So your branching program is going to just look like something like, in fact, it's going to be like in fact, maybe I'll use a new page. So it's going to start with this, and then it's going to read every possible input like this. And it's going to have, yeah, so maybe, so it's going to have like 2 to the n sinks, 2 to the n sinks. And the sink, so the sink corresponding to x is labeled with a 1. So what is the sink corresponding to x? Well, that is like exactly what the sink that you end up with when you read this x n bit binary string x starting from the source vertex, right? And here you can label this with accept or reject, accept or reject. And how do you label this as accept or reject? Well, you just label them accept if that string x exactly encoded a halting Turing machine. Yeah. And so this is a very simple branching program for, I mean, this will work for every length, right? I mean, you can, yeah. But the point is that, of course, for every input length, you have a different algorithm here. And each algorithm, I mean, this branching program has, what is it? It could have width 2 to the n, because like towards the end, like, you know, this width could be 2 to the n. And the length is just n, right? Like, because it's just, you read x1 here, you read x2 here, and so on. And finally, you read xn. Amal, this is what you're saying, right? I mean, that, you know, just give this.
Yeah.
Yeah, exactly. So just notice that in the unary setting, the only difference is that somehow, because there's only one string of that particular length, it's either there in the language or not that language. So in that sense, it's an efficient program.
Yeah.
The unary program is efficient. In fact, it's a constant size program. Yeah, but again, yeah. So anyway, so all right. So should I stop here for 15 minutes?
Yeah. We started at 10:05.
Right.
So now it's 11:06. So maybe we can join back at 11:20 and wind up at
maybe
12:10 or something.
Sounds good. Yeah.
Yeah. So we
Okay.
join back at 11:20.
Okay. Sounds good. Yeah. Maybe I'll stop sharing.
Yeah.
Uh,
So for the making that layering, is it just enough just to introduce? So let's imagine you have a uh, edge from layer I to layer I+2. You
yeah.
insert a dummy vertex in layer I+1 and
Right.
just duplicate that. That
Yes.
that's enough, no?
Yes, that's enough.
So for instance, if the edge label is X, XI, you put
Right.
XI.
Yeah. 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 That's enough. Yeah.
Probably you will have to, yeah.
I mean, you have to take care of little things. I mean, so if you wanted to also make sure that you're only querying a single variable in a particular layer, then you might have to add dummy nodes
Yeah.
and say, okay, do nothing kind of nodes, like uh, yeah, but that's enough. I mean, yeah, or you can slightly stagger the computation, so to speak, because yeah, in the main resource in branching programs usually is like width. So, and for a good reason, I'll explain why. um, so as a result, you are always looking to layer, put normal forms, and do so things so that you are always stay within like some particular width that you want. Yeah. uh, so let me just state this probably. So before that, I wanted to do a couple of more examples. So okay, so I did this theorem about in this halting problem and so on. But in general, I wanted to just say that
By the way, what is straight line programs and why is this thing called branching line programs?
sorry, straight line programs are basically circuits. They are nothing but circuits. Straight line programs are, so I don't know what is the right reason behind the terminology. I think the way they initially started out was something like when they wanted to start. The definition of straight line program is as follows: you start with some register, let's say x1, you load with something, some maybe 0, x2, you load with something, maybe 1, and then x3 is something like so every step that you do next is like some operation of some things that you previously computed.
Okay.
So in that sense, it's a straight line, I guess. I don't know the reason behind the terminology, but what a straight line program really captures is actually a circuit. And of course, depending on the operations that you are involved, I mean, they come up in different contexts. I mean, we can define a straight line program or monoids like groups,
Yeah.
or like or the general straight line program in complexity theory is usually circuit.
Yeah.
And or yeah, right. Branching program, because like this branching programs actually started out as like a generalization of this what is called decision tree. Like you can think of the branching program as like a more succinct sort of decision. A branching program is essentially you take the decision tree and identify all the 0 and 1 vertices, the leaves. What you should get is a decision tree, the branching program. I mean, sort of like it's a compact decision tree, so to speak. So for example, if you looked at a decision tree for parity, it will have exponential size, right? I mean, it will do something. If x1 equals 0, it will do this. X1 equals 1, it will do this. And then it will go to the next node, right? And then it's not really, so in a branching program, the way you do it is you sort of identify, you say that, okay, anyway, finally, these guys at the leaves are going to be labeled with 0 and 1. So basically identify those nodes, keep shrinking the intermediate nodes up to this equivalence of, basically because it's just keeping track of mod 2, right? So yeah, so I don't know, yeah, branching program, yeah, I guess that's the probably because it comes from some sort of a tree structure, the decision tree.
So branching programs are really like flowcharts. Yeah, it's just
Yes. I mean, or the other, they're also called this OBDDs, ordered binary decision diagrams. And yeah. So they're not. I mean, yeah, we can think of it as a flow chart. Yeah. But they shouldn't have loops.
Yeah, they shouldn't have loops. It's just yeah,
Yeah.
a
It's a
cycle.
DAG. Yeah, it's a DAG. Yeah,
Yeah.
it's a DAG. Yeah. Right. All right. So, okay. So I just wanted to mention this particular, probably a simple thing. I mean, so just I want to do this example basically. You can do, let's say, let's look at an branching program for the AND function. Right? It's just it has to be one only when all the inputs are one. So that will be something like you start at the start state. Whenever you keep reading x1 equals 1, then you go and then you keep doing this. Keep doing, and then finally you end up, after you read all the inputs and all the inputs are 1, you have a end up in an accept node. And from here you have a sync to a, let's say, a reject node, which is like whenever you see a 0, right? And so this is a simple branching program for AND. And similarly, you can have a branching program for OR. The only thing is the accept, and it'll be the same thing, except that now, even if you see a single one, you accept, otherwise you reject. Yeah, this is a um, this is a branching program for yeah. So this is a branching program for OR. Yeah. So as a result, I mean, like you can compose these AND and ORs together, and you can come up with any Boolean function. Like you take your favorite Boolean function on the nth slice of your Boolean function. It's from 0, 1 to the end to 0, 1. And corresponding to this, you have a truth table, right? Whenever x1, x2, xn, and then here's the value of f. And this has 2 to the n rows and n columns. And some of these are 1, right? And you basically what you do is you just you just check whether this input is, you look at all the ones in the in this function column, and for corresponding to that, whichever input is there, you just take an AND of these things, and you use a branching program to compute this AND of those things. And once you have the AND of those things, you use an OR too. So basically, you can write any Boolean function as an OR of AND of this is like called this min-term representation, DNF representation or whatever, in DNF form. This corresponds to exactly whatever, maybe this corresponds to, yeah. So this particular row will go into this, and will be the variables input to the AND gate, and you OR over all the ones present in the truth table. And this is a valid I mean, this is a simple, I mean, any Boolean function can be realized in this way. And in particular, because you have realized AND and OR using these branching programs, you can just compose these things together to get a branching program for your function. Okay, so in fact, so this just shows that uh, constant, and because this and OR are constant with branching programs, can compute any Boolean function. The exact constant, again, we can go and optimize it and think about how to do this. I think, in fact, if I understand correctly, with 3 or 4 should already give you, with 3 branching programs, in fact. Yeah. Any Boolean function. Okay. So, but of course, this implementation of via will take the size will be roughly 2 to the order n. Why is that? So because I mean, yeah, because you're doing this naively, you're implementing this for every input. So your branching program will have exponential length. Yeah? So that's unavoidable. Yeah. So in fact, what we can show is that
I didn't understand how you use this and or.
right. Okay. So maybe I'll just
Can
yeah.
you just show for the parity?
So which one?
For the parity function, can you show us how will you convert
Right.
that?
Yeah. So basically, the idea is I first compute uh, an and of these things. And how do I do it? So I start in the start variable. Uh, so now what I'll do is if x1 equals um, sorry, so this particular, so okay, so maybe one, so let's look at this particular input, which is like, let's say there's a one on this input for your branching program. So your Boolean function, let's say, accepts this input, one followed by n minus one zeros. Okay, so this, what I'll do is, so or rather maybe x2 bar equals one, right? And you go here, and then let's say, so this is an accept. So this just realizes the fact that I mean, the nice thing is, like, based on the and, you can basically build a branching program that accepts any string you want. So that's the main idea. So if, for example, here, if x2, just right there, any mon, oh yeah, x2 equals 1, except x2 equals 0, and x3 equals 1. So this is a branching program that exactly recognizes this particular input, right? It 1 followed by n minus 1 zeros. Everything else is rejected by this thing. Yeah. So my branching program is going to, what it's going to look like is, I have branching programs for all of these. So so maybe this is for this one followed by all zeros. Similarly, you can have a branching program for, let's say, 1 0 1 0 1, alternating ones and zeros, right? So let's say I have this branching program built. So this, how will this look like? This will again look like x1 equals 1, and then here in x2 it has to, this has to be x2 equals 0, otherwise it has, for x2 equals 1, if it reads, it should reject it, right? And so on. And finally you have this x. So now what I'll do is, I'll combine these two into, let me call this y1, let me call this y2. I'll combine these two into an OR gate, like this, right? I mean, so what I'll do is, I'll so I'll, okay, so one second. So maybe an easier way to, if you wanted to see constant width, this would so how do I, okay, so okay, maybe I think I'll, so yeah, thanks for pointing it out. So maybe I'll do a more general theorem which says that so if you have a Boolean function f, and if you write f as f1 or f2, let's see how to come up with the branching program for f1 or f2. Okay. In general, the way you do it is like, so how does this work? So this branching program, so it should output a 1 if either f1 or I mean, either f1 or f2 output a 1. At least one of them outputs a 1, right? It evaluates to a 1. So what I do is, like, let's say so one second. So what does this mean? So basically, you have saying that there is a branching program for f1 means that there is a graph, a DAG, right, with S. And let me also say that there's only one sync vertex. And as an exercise, you can actually try to do this, that if your branching program, any branching program can be converted to a BP with exactly one sync. If it had many syncs, you can just replace it by one sync. And we can call this S. So maybe I'll call this S1 T1. And similarly, let's say you have S2 T2. Right. So now, if I wanted to take an OR of these two, so what does it mean when this branching program with source S1 and T1 recognizes F1? Well, that means that for the setting of the variables, there is at least one. If F1 evaluates to 1, then there should be some path from S1 to T1 in this branching program. Similarly for S2, right? Now, if I wanted to implement OR of these two, what I'll do is I'll create a new source vertex, right? S, and then connect it to these two things. I'll just start at both these things. And I just want to make sure that there is one path from S to, and maybe again, I'll connect these two to P. Okay, so okay, so maybe I think when I say there's exactly one sync, what I meant is one. So there can be like many syncs, but what I meant is one accept sync and one reject sync, and I'm connecting the accept syncs. Okay. T2 is where it accepts. Maybe there's a different sync where it rejects. I'm not connecting that. Yeah. So I just connect these two, and then so notice that if so on this I label by, let's say, 1. Okay. So now if a string, so let's look at this f evaluated. I mean, it takes a Boolean input x, and this is f1 of x or f2 of x. Now let's say so what happens, like S1 reads x here, S2 reads x here, right? And if both these, so if let's say one of these accepts x, then that means that there is a path from S1 to T1 or S2 to T2, right? One of these here there's a path, right? And hence there is also a path from S to T, because this anyway is, I've connected it with this label 1, right? So sorry, is there a question?
No, it's just Remit joined, that's all.
Okay, okay. Right, so as a result, now F1 of this is also will evaluate to 1. So this is exactly this construction. This is called what is called a so the name for this construction is actually there's a name for this. This is called a series parallel construction, because I'll come to the parallel part soon. So basically, if I had branching programs for F1 and F2 separately here, then I can do the OR of them by basically, because that by definition, the acceptance of branching program is via reachability in a graph, right? So I can construct another graph, and such that the reachability in this graph gives you this OR of construct this new graph with these two graphs for F1 and F2, such that reachability in this new graph, this is exactly this branching program realizes.
I have a question.
Yes,
So,
yes.
So here S on 1, it's non-deterministic. The choice is non-deterministic. Yeah.
Yes.
But so far where we were considering, it was not non-deterministic.
So I didn't specifically bring up this point in the sense that because I thought it will only come in this. But the thing is, like, by definition, there is the branching program that I've defined before. It is not required, though the example that I gave, the parity example I gave was deterministic. It's not required that this be deterministic. For example, so just let me just go back to I started out with this example, but I just thought let me not make it too complicated. So for example, here I did x1 equals 1, x3 equals 1. I could have just had maybe x2 equals 0 here. And this is just not defined on x1 equals 0. All these things are completely fine. So this is, so there is, sorry.
That is fine, because still you are exactly at one place where you start when you started somewhere.
Right. No, so for example,
Oh,
what
yeah,
happens
yeah,
if
yeah.
x1 equals 0?
Yeah. It can both be. Yeah, like you are saying that x1 could be 1 as well as x2 could be 0. So where will you?
Right. Yeah. So all you need is that there is some setting of variables such that makes this st path come alive, right? So there is a yeah. So in that sense, yeah, for a given input, if there is some path which leads to which leads to an so if there is some st path, source to accepting path in your graph, then your branching program accepts. And it need not be that the labels are like it's complete, like it's not be deterministic. So there you can make this distinction between deterministic programs and non-deterministic programs. And in fact, I think for constant, like exactly for yeah, so in our case we'll just deal with deterministic programs for now. But good point, like this is you can also talk about NBPs, like non-deterministic BPs versus deterministic BPs. The P versus NP question sort of thing you can ask here as well. Yes.
And anything is known about this?
I think I mean I'll come to this, like, yeah, so I'll talk a little bit about this. Yeah.
Okay. And also there's the construction which you said
Yeah.
for this and or, you said it's width is 3, but this lemma does not give you width 3.
Yes, exactly. That's because I started with the DNF representation. So 1 second. So right. So 1 second. So yeah, so that is because see, if I can also represent any Boolean function as a CNF, right? Like I can also represent this as a CNF. And so let me finish the AND construction that I just did the OR construction. So let's see how the AND construction look like. It's exactly the same thing, except that now you put this in series instead of, so here we put this in parallel, right? So if I wanted F1 and F2, then I would just do this. I'll join the let's say the S1 T1, the sync node of the accept sync node of F1. I will join it with the start node of F2. So T1 equals S2. Yeah. And then finally this is T2. Okay. So now if there is a path in both F1 and F2, then only then there will be a path in your new branching program. So this is an AND construction, right? So so now if you wanted, so notice the nice thing is that so as Amal pointed out, like this, if I wanted a constant width branching program for, so I claimed here that there is a constant width branching program can compute any Boolean function. But notice that if I started out my Boolean function in this way, right, then what happens is because it's an OR of ANDs, and with OR, every time I include a new term in my OR, so for example, when I did F1 and F2, this width blows up, right, by twice. Like it will be like the width will be width of F1 plus width of F2. Yeah. So let's just analyze this this construction. So here, this uh, width of this function f is at most width of f1 plus width of f2. And in general, since we have, if you notice this DNF representation, we have 2 to the n ORs. This is up to 2 to the n or 2 to the n minus something like 2 to the n, up to 2 to the n. So as a result, our width becomes exponential in this construction. But notice that what you can do is, instead of, you can also write any function as the same thing. You can write it as AND of ORs, where now you're picking out the zeros instead of the ones and finally negating it, right? You're recognizing the zeros and then flipping the sign of the yeah. So basically, so okay, or another way to think of it is like you can use De Morgan's laws to push the negation to the bottom, right? And in this case, what you have is an AND of ORs. And when you have an AND of ORs, then you can implement it in constant width. Why? Because the width here is the max of width of f1 comma f2. Okay. So as a result, yeah, maybe +1. You might need a +1 to no, maybe not. Maybe it's just very max. So as a result, you can actually use this construction instead to come up with any Boolean function. So what do? You go to the truth table. You look at so basically this truth table. Um, you can just use De Morgan's formulas to push the negations to the bottom. Yeah, is that clear? I mean, like, so this is basically you output a 0. I mean, you add the output of all the zeros, and then you is it clear, Amal?
No, I mean,
Okay. Oh, sorry. Okay, so maybe I'll just repeat. I'll write a new page. Okay. So okay. So let's look at the parity function, for example. So you have 0 0 0 1 0 1 0 1 1 1 1 0. So now what I'm saying is I can also recognize the function at these wherever it outputs a 0, right? I mean, like, I mean, so this function it's essentially whenever so where so okay, so maybe let's write it as, so originally we wrote it as OR of ANDs, and now we want to write this as so it will be fine if we can write this as AND of ORs, right? So what I'll do is, but you know that so if I have A or B, right, then this is the same as A or B double negation, right? And this is what? This is just A bar and B bar, right? Is that clear? So now what I can do is, this is an OR of a bunch of things. Now I can just write this OR as AND of so basically I can use a double negation, and then I can write this as AND of ORs, right? I can so I put two negations here, right? And then I push this negation inside, right? And if I push this negation inside, what happens? So this is like so so let's say there are all these midterms. So now what will happen? This when I push this negation inside, so I will have this gate is going to become an AND gate. And so basically, so is this familiar? This is De Morgan's laws. This is basically, I'm just using De Morgan's laws. So it becomes AND of for the negated, and then you just push, and here you're just pushing the, again using the De Morgan's laws to push the negations. Right? Is it clear? Sorry, I mean.
Yeah, that is clear. But if I just look at the truth table, like you said,
yeah,
like if I pick the min terms, the terms which correspond to 0,
right.
Can I just construct it directly from the truth table just by looking at the truth table? This
directly looking at the truth tables. So you can. So okay. So
just like
so
for the CNF case.
Yes.
No, for the DNF case, I just looked at ANDs,
Yes.
terms which correspond to my one, which is the max terms, and
Right.
they just took the OR.
Yes.
Yeah.
So I mean, you can also do that, right? I mean, like then you're essentially swapping the accept and reject states at the end. I mean,
So how do I do that? How do I do that?
so basically what you do is you take all the zeros here,
Mm-hmm.
and you're taking now, and okay, so let's write it down. So you have N and you have an F, and then let's say you have, right? So and now, so your function is like 0 at exactly these points. So what I'll do is, uh, so how do I do it? So let's say wherever it is 0, so let's say I create a, I create a mint, I create a, so so I do this, right? In all these places it's 0.
Mm-hmm.
And now whenever it outputs a 0 somewhere, no, so okay, so this is,
So I have to negate this program. That's all I have to do. Yeah.
yeah, I have to negate this program. I mean, whenever, so yeah, if I run this thing on my program, and if it accepts, then I reject, and if it rejects, then I accept. Right?
Mm-hmm.
Yeah. So I mean, but this is you can do this by composing with the, I mean basically I'm saying like just implement this function, right? I mean this function exactly is going to capture the zeros of this function. And whenever, so basically what you do is you take your program, and whenever your program leads to a reject, you accept it, otherwise you accept it. Is that clear?
Yeah. Yeah. Yeah.
Yeah, basically it's the same
Okay.
thing.
Okay. So what what I
So
understand.
maybe then you have to be careful about this program also has a reject sync, right? So you have to be careful, you have to maintain that sync and turn it. I
So
mean,
yeah. So to in conclusion, like if you want constant width, you go for uh,
CNF.
CNF, and if you want constant length, you go for DNF.
Yeah. You with the DNF you will get not constant length, because
Not constant.
ideally it
I mean like about the
is
small width.
small length. Yeah, this will be length will be n+1 in this. I mean, sorry, for the arbitrary, yeah. If you wanted the length to be small, just a polynomial in n, then you go for the CNF construction. Yeah, but the width will blow up to exponential 2 to the n. Yeah, is that clear? Okay, so all right. So okay, so how much time is remaining?
10 more minutes.
Okay, sounds good. So maybe I'll just quickly okay, so let me just see what else I want to say. Okay, so there is this okay, so I just conclude with like saying why there's a very concrete way in which branching programs are related to space of an algorithm. I mean, just as how like we saw that finite state automata naturally capture state of an algorithm, but also branching programs do. So because one way you can think of a branching program is like and especially the width of the branching program, you can think of the branching program as somehow like updating a register, right? I mean, like you have a register with some contents, like let's say a few registers, let's say, right? And then what you're doing is every time, so you start at a particular register, and every time based on so you can think of your graph as sort of updating this register. It reads a particular variable and it updates a particular register, reads a particular variable, updates a particular register. And so in that sense, you can think of branching programs as sort of capturing the space of an algorithm. In fact, to be more precise, space uh, usage of an algorithm is actually order log of width of p. So why is this the case? so notice that, okay, so there are two ways to it, right? I mean, if I had a log width BP, then, so if I had, sorry, width WBP, um, uh, so width WBP, then this should correspond to at most 2 to the W space. Oops, sorry. Order log W space. And in the other way, if I had an algorithm which uses order log W space, then I should be able to come up with a 2 to the W width. So the idea is quite simple. Like, so let's look at the space to width idea first. So what is the main idea here? Well, if your algorithm uses order log W space, then there are potentially 2 to the W configurations in your. So I mean, so basically, if you know a bit of, so there are 2 to the, if you have S tape cells, then there are 2 to the S possible configurations of your tapes, of your memory, right? Of your memory. So here again, memory, it's like I'm thinking of it as a collection of bits which you keep updating and you can store some information. Yeah. And now you create a vertex for every such, create a graph for every configuration. Right? With the graph with the vertex for every configuration. Okay? And you put an edge, and you have an edge if you can move between two configurations. Two configurations. Okay? And this clearly is enough. I mean, this is, I mean, so if you did this, I mean, what you would get is by definition a branching program, because also whenever you have a okay, one algorithm. So one assumption I'm making here is that your algorithm is a finitely terminating algorithm, right? If algorithm assume algorithm is finitely terminating. Yeah, because in that case there is no cycles, and so there is no repeat in configurations. So essentially, what you get is a DAG, right? So you get a DAG. Yes, and this DAG has, I mean, it's basically you can just verify that this is an in-meter branching program. So for the other way, well, if you had a width, if you had a width W branching program, how can you traverse it? I mean, how can you traverse it in order log W space? And here, really, what we are saying here is like this algorithm is actually has to be non-deterministic. Right? I mean, in fact, the equivalence is width W branching programs actually capture order log W space. So as a result, branching programs actually capture this complexity class called NL. With poly branching program actually capture this complexity class called NL. And why is this the case? So, well, basically, let's say if you had a width W branching program, okay, maybe
I have one question.
Yeah.
If you have a width W branching program, and
Right.
let's imagine it's also layered.
Right.
So at some point I can have, it's not deterministic. Yeah. So
It's not necessarily deterministic.
So if I have only log W space, then I will be able to index only one of those vertex, no?
Yes, yes, yes. But right. But the nice thing about with this branching program is that with non-determinism, you actually only guess a path. So you only guess. You
Okay,
just
so when you say all order of log W space, you mean non-deterministic space.
yes, yes, yes.
Okay,
Right.
all right.
Right, right. And exactly, and this is the reason because the complete problem for non-deterministic space NL is exactly directed reachability on a graph.
Mhm.
Right? So NL is this class which is like with exactly captured uh, by reachability in a directed graph. And and uh, and you can solve this problem of reachability in a directed graph in NL. And the way you do it is you basically um, uh, order log W space uh, is sufficient uh, to guess vertex at every step. Guess again, this non-determinism. I mean, so clearly there is a crucially uses non-determinism vertex. I mean, basically, it guesses a path, or rather, I should say, it guesses a path vertex by vertex. And ST path vertex. So, in that sense, this is a very precise characterization. If you have, if you can exhibit a width W branching program for your problem, then you are inherently giving an order log W non-deterministic space algorithm, and vice versa. Yeah. Okay, so but for us, we will be only after this concerned with constant. So the reason I didn't really go into uh, non-deterministic branching programs to begin with, at least, was because for us we'll be concerned only with constant width branching programs, and there these are the same things. So so let me stop here. Tomorrow I will start with. So remember. So just to recall, I'll just summarize what I said so far. Um, so our main goal to begin with was to come up with the. Maybe I'll just scroll up. We said our main goal was to come up with the answer this question. Basically, is there a way to compute or decide this majority function using a constant amount of space? Right? You know that if you actually allow uh, something like, oops, maybe if you allow login bits of if you allow to store so much, then of course you can compute the majority function. And we saw a bit about this constant space algorithms, which are like this finite automata, which was seen before. So and we said, okay, so it's clear that I mean by some pumping argument you can show that majority is not a regular language. It cannot be determined by decided by finite state automata. So I didn't completely make this precise. But what happens is when you have so of course like so what we said was, okay, there is a way to actually model constant space algorithms, and this for this we needed this notion of non-uniform computation, where you actually allow not just one algorithm but like different you can have different algorithms, completely unrelated algorithms for different input lengths. Yeah. And finally we showed that like using this we generalize this finite automata to its non-uniform counterpart, which is exactly this model of branching programs. And using this branching programs, we I mean, of course, these non-uniform models can compute a lot of weird functions like I mean, uncomputable functions also can be computed. So it's not a wise thing to use this to design as an algorithm design tool. But still, it's a very nice way to like think about a new computational model. And we can also make sure that this model doesn't compute weird functions by putting what I called uniformity conditions, which I'll come back to towards the end. There is ways to enforce what are called uniformity conditions to recover back to essentially preclude things like this halting problem being computable by this thing and so on. or to give unnatural power to this model. And finally, we saw that in some sense, this actually captures a notion of space. So from the next lecture, I'll introduce one more non-uniform model, and we sort of look at how this model relates to this branching programs. And finally, hopefully, using that, we'll move towards answering our question about majority. Okay, so let me stop sharing here.
Actually,